personas que tenemos dando la charla en este ciclo de conferencias en honor a nuestra compañera Patricia, y es más orgullo todavía para mí poder presentar a los dos. Son dos excelentes científicos, son dos excelentes personas, y voy a empezar presentando a Ingrid, que es la primera que nos va a dar el seminario. Soy Ingrid, actualmente catedrática en la Universidad de Leuven, en Bélgica. Ingrid, su tema de investigación fundamentalmente es el análisis de supervivencia, aunque ella ha trabajado en distintas ramas de la estadística, con una fuerte componente en la inferencia no paramétrica y semiparamétrica, y algo que destaca de la investigación de Ingrid es la componente teórica. Le gusta la teoría, le gusta la formalidad, pero quizá lo más relevante es que la teoría no se queda solo en teoría, sino que todo lo que hace Ingrid tiene una repercusión en la práctica muy grande. El impacto es muy grande y tiene aplicaciones pues, no solo en los campos propios de la supervivencia, la medicina, la biología, la medicina y demás, sino también en el campo de la economía y de la economía. Entre los temas que destacan que he comentado, la charla que nos va a dar hoy pues, trata sobre esta inferencia causal y las variables instrumentales. Aparte de la investigación, pues tengo que destacar pues, la investigación que ha publicado Ingrid alrededor de 200 artículos, ¿no? La investigadora que tenemos aquí pues, de alto nivel, ha realizado una tarea de las revistas actuales, pues fue coeditora jefe de la revista de la Royal Statistical Society CLT durante varios años y actualmente editora asociada de HASA, de ANAS en estadística, de biométrica, de Electronic Journal of Statistics, de modo que tenemos una investigadora de muy alto nivel. Entre los reconocimientos que ha obtenido Ingrid, pues Fellow de la American Statistical Association, Fellow del Institute of Mathematical Statistics y miembro elegido del International Statistical Institute. Y muy recientemente, que tuve el honor de estar allí también, pues fue nombrada doctora honoris causa por la Universidad de La Coruña. Eso fue justamente en junio del año pasado. Así que muchísimas gracias, Ingrid, por estar aquí. Thank you very much, and we look forward to hear, to listen to you talk. So thank you.
Thank you very much, Lola, for the introduction, and of course, thanks also for your hospitality this week and for the nice collaborations that we have this week, but also in the past. It's always a pleasure to come back to Granada to work together. So I will talk about joint work with one of my former postdocs, Keilegom, and also this work is together with Jean-Pierre Florent from Toulouse, and with Samuel Centurino, who is from Stony Brook University in the US. And so this work is on survival analysis. That's my main area of research, and I'm going to combine survival analysis in this talk with causal inference. So we will have data from an observational study, and we want to infer causal relationships based on an observational study. And the question is how you can do that. Okay. Oops. Doesn't work. Is it on? Yeah, I can use the arrows. Yeah, that's right. Yeah, okay. Yeah, okay. So, we will start with an introduction just to explain the context and give you a bit of a bit of information about how we are going to deal with this causal relationship. And I will start with a simple case where we have a survival time, T, and a binary treatment variable, C. Now, this is not what we are going to do later in the talk, but it's just to start with a simple example. So let's say that we want to know what the effect is of the treatment on the outcome T. And we have two difficulties. The first one is that T is subject to right censoring. And the second one is that Z is endogenous. And endogenous means, broadly speaking, that we have an observational study, so the treatment is not randomized. And so you need to take this issue into account. And the way we will do that is by using a so-called instrumental variable. So let me maybe first explain what this means, endogeneity and instrumental variables. Okay, so the whole problem is about this difference between a simple correlation. Correlations can be identified very easily, but we want to have a causal effect and not just a correlation. And if you have an observational study, then these two things are not the same. Right? So this is a well-known problem, and so for instance, it's important not only in statistics or biostatistics, but also in economics. In fact, the Nobel Prize of Economics in 2021 was given to Ingrid, Imbens and Card exactly for their work on causal inference in economics. So, as I said, we are going to use an instrument. Now, what is an instrument? It's a variable that is related to the treatment variable. The stronger this relation, the better. And this variable should be randomized. So the treatment itself is not randomized, but this instrument should be randomized. And the hope is that by having an instrument that is randomized and that is closely dependent on this treatment variable, we can identify the causal effect of the treatment on the outcome. And here is an example to illustrate the idea. So let's say that we have a medical study with two treatments, and we randomize the treatments, let's say treatment 1 and treatment 2. We randomize these treatments to the patients in the study. Yeah? Now, treatment 1 is, let's say, an experimental treatment, and patients might refuse this experimental treatment. And if they refuse this treatment, they are given the standard treatment, which is treatment 2. Yeah? So, suppose that we have a hypothetical example in which we have 400 patients, and at the beginning each treatment arm has 200 patients, but let's say that 50 of them in the first treatment arm refuse the treatments. So the treatment that they receive is then going to be the second treatment. And so at the end you have 150 in the first arm and 250 in the second. Now the problem is that maybe the patients that refuse the first treatment, they are maybe the ones that are maybe not, or let's say it the other way, those that accepted the experimental treatment are maybe the ones that are very ill, because they are willing to take the risk of taking an experimental treatment. Yeah? And so it means that after you put these 50 patients in the other treatment arm, you don't have a randomized experiment anymore. And you need to take that into account. And the question is, how do you do that? So that's, roughly speaking, the problem. And so in this example, the treatment Z is going to be the treatment that patients receive at the end. And the instrument is going to be the treatment that you assign. Yeah? And these two are very much related, because for most patients, the assigned treatment and the received treatment are the same, so they are clearly very much correlated, but the assigned treatment is random. So this is exactly what we expect from an instrumental variable. It's something that is done in a random way and that is correlated to your treatment. Okay, so roughly speaking, we have this situation, we have the outcomes, we have the treatments, and so the problem is that we have some variable u which influences both the treatment and the outcome. And that we don't want. So in our example, this U could be the health of the patient, because this health is going to influence both the treatment that he will at the end receive, but it will obviously also influence the survival time. Yeah. So ideally we don't want this U, but it's unfortunately there, and so we are going to solve that problem by using this extra variable W, which is in our case the assigned treatment, and so W has a correlation with the Z, the actual treatment, but it's randomized. So it only influences the outcome via this treatment that patients receive. Okay, and so now you might wonder, how do you deal with this problem? So how do you take this endogeneity into account? Now here are a few maybe naive ideas. So you might just ignore this problem, and then you might take a linear model where you use the treatment. So you ignore the fact that the treatment is no longer random. Yeah? And in a classical linear model, you might assume that the conditional expectation of the error given this treatment is 0. But that's actually wrong. And the reason why it is wrong is that you have this correlation between the treatment and the error or the unobserved endogeneity, which I called in the previous slide U. So this U is actually now epsilon 1. So this is a wrong model, because in practice this conditional expectation will not be 0. So you might then say, okay, let's not take Z, but let's take W. So for W, indeed, we have this property, the conditional expectation is 0, but now the problem is that we are not interested in the effect of W on the outcome. We are really interested in the effect of the received treatment on the outcome. So also that this is not a correct model. So what is a solution? Well, we are going to work with this model because this is really the relation that we are interested in, but the assumption on the error is that the conditional expectation of the error given W is 0. And that's because we are assuming that the W is completely random, and so the conditional expectation of the unobserved heterogeneity given W, this is 0. Huh? So if you make that assumption, then you can easily see that the identifying equation is going to be this, which looks very much like the normal equations that you have in linear regression, except that you have here the W instead of the C. And in that way, you will be able to identify and to estimate in a correct way your regression coefficients. Yeah? Okay, that's a simple example where we have binary Z and binary W. Now we come to the problem that we want to address in the paper, which is more complicated. So we still have a survival time T that is right-censored by C. But in our paper, the treatment is not binary. It's actually a continuous variable, and it's even dynamic, because it's the time until the treatment starts or the treatment happens. And the fact that it's dynamic or that it's a time has the consequence that it might also be censored. Because you have your time axis, you wait until the treatment starts and you wait until the patient dies. And the patient can die before the treatment starts. And then this Z variable is censored by T, or it might even be censored by C. And that's a problem because obviously the treatments and the outcome, they are related. So this is not independent censoring, it's dependent censoring, because T and Z are related. No? Okay, so that's the problem that we have to consider here. How do we deal with this dynamic treatment that might even be censored? As in our previous simple example, we again assume that we have an instrument, W, and here are a few examples in which this setup might occur. The first is the simple medical context where you have patients and you want to know when they die from a certain disease. And then the Z variable can be the time at which they get surgery or the time at which the treatment starts. Yeah? And this moment Z can be endogenous, for instance, because a patient that is very severely ill might have a higher priority on the waiting list for surgery, let's say. So the time to surgery or the time to start of treatment might not be random, but patients that are very seriously ill might get surgery earlier. And so again, the health of the patient will have an impact both on Z and on T. And so you have an endogeneity problem. Another example comes from economics. T can be the unemployment duration, and Z can be the time to reduction in unemployment benefits. Now, this context also leads to endogeneity. For instance, if, and this is actually happening in France, for instance, the law for unemployment benefits changed recently. And people could choose whether they stayed in the old regime or the new regime. So it was a choice of the person himself. And the new regime was actually pushing people more to find a job. So if you are a person who is not very motivated to find a job, then you will stay in the old regime. And so the motivation of a person will have an influence both on the time to this reduction in employment benefits and also on the unemployment duration. Yeah? So that's another example where we have exactly the problem that we want to address. Okay, here is then a few words about the censoring issue. So as I said, we have T that can be censored by C, and this censoring mechanism is assumed to be independent, so T and C are independent. But the fact that Z can be censored by T or C, this is dependent censoring because Z and T are correlated. Yeah? And we have to deal with that. So here are a few cases, but there are actually many more because you have a Z, a T, and a C, and they can occur in any ordering. Yeah? In most cases, like for instance the last two, there is an independent or exogenous censoring because if T is censored by C, there is no problem. This is okay. But the difficult situation is this one, where Z is censored by T. So the person dies before he gets the treatment. And that's causing an issue or a problem because T and Z are correlated. Okay, here is the empirical application that I will consider at the end. So we have data from a Belgian insurance company, and it's a study about medical leave for burnout. And so patients or people working in Belgium, they have, let's say, they are medical leave because they have a burnout, and the insurance company wants to know how long it takes before they go back working. So of course they are very interested in that because it's an insurance company, so they want this duration to be as short as possible. Now, what is the endogenous variable, or what is the treatment variable? It's the time between the start of the medical leave and the beginning of a therapy for burnout. So a patient, at some point, he stops working, and then, of course, he does not get a treatment immediately. There will first be it will be decided whether a therapy for burnout is necessary, etc. So there is some time before the treatment starts. Okay, so that's the context, and there is censoring because the study ended at the end of 2020, and so some people did not start a therapy yet, and some people also did not go back working yet, so they are censored. What is the instrument here? So remember, an instrument should be a variable that is related to the treatment variable and that is randomized. So in our case, we take a variable that tells you a proxy for the availabilities of the assigned medical center. So there are many medical centers to which people are sent to in order to get treatment for their burnout, and some centers are more busy than others. And so for some centers it takes longer before this therapy starts. And this assignment to these medical centers is done based on geographical location of the patients. So you might say that this is random. There is no endogeneity going on here. And this availability of the centers is clearly related to the duration between start of medical leave and beginning of therapy. And since it's randomized, it's a correct instrumental variable. Okay, I didn't say yet why we think that Z is endogenous. So why is it endogenous? Because some people might refuse to receive treatment. And also sometimes a treatment is not given if the center thinks that the treatment is not useful for a certain patient. So there is endogeneity in that sense. Because again, the person can decide not to follow the treatment. Okay, and so of course we want to know what the effect is of this treatment variable on the survival outcome, because this tells the insurance company whether following this treatment for burnout is useful to reduce the period of medical leave. They want to know whether it's important to invest money in these therapies, yes or no. Okay, so here is a schematic overview. So a patient, when his medical leave starts, he's assigned to a medical center based on geographical location. This medical center will do an evaluation of the situation of the patient. Sometimes the medical center decides that a treatment is not useful, and sometimes they decide to offer the treatment. And when the treatment is offered, the patient can either accept it or refuse it. Yeah? And so there is endogeneity because they can refuse the treatment. Yeah? And then they are followed over time until they go back working. And that's the outcome variable. Here are two papers that are a bit related, but they are not exactly doing what we are doing. The first one goes back to 2007. It's also about dynamic treatment variables with endogeneity, but in this paper there is no censoring. So there is not this issue of censoring that affects both the treatment and the outcome. And then in this paper by Gerard van den Berg and co-authors, they assume that the treatment and the instrument are the same, or the treatment variable is infinity. And that's not our context. In our case, the treatment and the instrument are different variables. Okay, here is then in a nutshell what we are going to do. So we are going to try to identify and to estimate these causal effects of the treatment on the outcome. Now, typically in this context, you cannot use likelihood methods, for instance, because the data that you have are not representative for the population that you're interested in because of this observational nature of the data. So instead of using likelihood methods, for instance, we are going to use a certain system of equations that we are going to solve. And these systems of equations will take this endogeneity issue into account. So in our case, we can have continuous treatments and continuous instruments, whereas in many other papers, these are assumed to be binary. We allow for censoring. We will identify the treatment effects for the full population, whereas other papers often look at the compliers. So the compliers are those that do exactly what the instrument is saying. So these are the ones for which the Z is equal to the W. And so, yeah, I think it has many applications. Our data example comes from labor economics, but there are obviously other examples. Okay, so here is then the more formal development. So we are going to work with potential outcomes. So potential outcomes are, let's say, theoretical outcomes if the treatment variable would be equal to a certain little z. So these are latent variables. You don't know what this tz is, except for the z that you observe. So the actual survival time t that you have for an individual is the one that corresponds to the observed treatment capital Z. Yeah? But you might have many other tz's for other values of your variable z that you do not observe. Yeah? And these are called potential outcomes. It's very typical in this causal inference framework. And so the T infinity is the duration if someone would never be treated. So someone who refuses the treatment, his duration time will be T infinity. Okay, now we are going to work with hazard functions, and here is the usual definition of a hazard function, except that we are using here the hazard of the potential outcome. So Tz is again this latent variable corresponding to treatment little z. So this hazard, which is called structural hazard because it's kind of the theoretical hazard of this latent variable Tz in the ideal world where you would observe this. This structural hazard is in general not the conditional hazard of T given Z. And that's because we have an observational study. So you cannot just take your data, T and Z, and estimate a hazard from your data. This is something different. Okay, so that's one issue, and then an assumption that we are going to make is this one. So if you have two treatment times, Z and Z prime, then the hazard it's going to be the same for these two treatment times as long as the time point t is less than these two treatment times. So what does that mean? It means that if I know that I will be treated in 1 month or I will be treated in 1 year, this is not going to influence my hazard today. So there is no, what is called no anticipation assumption. So your hazard today does not depend on when you will be treated in the future. Yeah? Which makes sense in most cases because normally you don't know when you will be treated, and so the hazard today does not depend on that. Yeah? So that's an assumption that we will make. And which is also made by other people in the literature, like in these papers. Okay, and this is what it means. So here you have your hazard rates for two values of z. So the red one is the one where you get treated at time 5, and the blue one if you get treated at time 7. And so the two hazards are the same until the time point 5. And so that's because, when you don't know when you get treated in the future, this will not influence your hazard today. Okay, so now, I see that time is running. I'm going too slow. Okay, I will hurry up. So now I go to the structural cumulative hazards. And this I will denote by u of z. And this is going to be my unobserved heterogeneity. And so this u of z will have an exponential 1 distribution. That's the usual thing, or the usual property. The cumulative hazards evaluated in your random variable has an exponential 1 distribution. So that's nothing new. And so the u can be, in our example, it was, for instance, what was it again? The fact of being motivated to go back to your job, or the fact of being healthy or not. This will influence both the treatment and the outcome. Yeah? Okay, now comes the second major assumption that we are going to make. So the first one was the no anticipation assumption. The second one is the so-called rank invariance assumption, which means that this unobserved heterogeneity does not depend on the moment at which the treatment starts. That's a very important assumption, and it allows to identify the treatment effect on the whole population. If you don't make this assumption, you can only identify the treatment effect on the compliers. What does this assumption mean? Well, you can easily show, and the proof is actually here, that it means that if you have two individuals, so let's go here. No. Here. If you have two individuals, I and J, then maybe for a given treatment time Z, individual I goes back to his work earlier than individual J. If you now give the treatment at another time point C prime, then the order in which they go back to work is still the same. They might go back to work at other time points, and the difference might be smaller or larger than here, but the order in which they go back is the same. That's what this assumption is saying. Yeah? Which might make sense in some situations, maybe not always, but in this context, we think it makes sense. Okay, so that's an important assumption. And now comes the endogeneity issue. So this unobserved heterogeneity, U, and our treatments, they are dependent, so that creates endogeneity. And so therefore we assume that we have an instrument which will be randomized, so it's independent of the unobserved heterogeneity, and it's sufficiently depending on the treatment. What we mean with sufficiently dependent is not clear yet, but it will come later when we look at identification. So here is our model now. So we have this structural cumulative hazard, which is the unobserved heterogeneity. This is independent of the instrument, and this unobserved heterogeneity has an exponential 1 distribution. So far everything is non-parametric. We don't make any parametric assumptions. We only make this rank invariance assumption and the no anticipation assumption. Okay, and now I'm going to rewrite my model a bit in a different way. So instead of defining the model via this structural cumulative hazard, I'm going to take the inverse. So I'm going to write the t as a function of z and u, instead of writing u as a function of z and t. And you can show that if you write t as a function of z and u, then you have this formula here. So what does the formula say? It says that if your t is phi 0 of u, then this phi 0 of u will not depend on the treatment as long as the treatment happens after your survival time. So this is exactly the no anticipation assumption. And if it happens before the survival time, then it does depend on the treatment. So again, these functions phi 0 and phi 1, they are non-parametric. The only thing we know is that they are strictly, and that the phi 0 does not depend on the z, whereas the phi 1 does depend on the z. Yeah? Okay, so we are going to work with this formulation, and we are going to try to identify the phi's, phi 0 and phi 1. If we have the phi's, we can go back to the lambdas, because phi is actually the inverse of the lambda. So it's very easy to go back and forth. Okay, and here are the data. So we have the survival time, the censoring time, we observe the minimum. We have the censoring indicator as usual. And now the treatment. So ideally we observe z, but actually z can be censored by y. So we observe a z tilde. And also this censoring indicator of the z, which is denoted by d, this can also be censored because we don't observe the t, we observe the y. So we have a d and a d tilde. Okay, so these are the data. And then we have, of course, also our instrument, which is fully observed. Okay, I think I'm going to hurry up a lot. So let's see, what shall I show you? So this is again the model. We want to identify phi 0 and phi 1. And the way in which we do that is by using this equation. This is a very central equation in the paper, which allows you to identify the phi 0 and the phi 1. Now, in this equation, we have an f0 and an f1, and they are defined here. And these are, in fact, something like the joint distribution of the survival time in the instrument. First, for the ones for which the treatment is smaller than t, so this is d equals 0, and then for the ones for which no, it's the opposite. D equals 0 means the treatment is after the survival time, and D equal 1 means the treatment is before the survival time. So you can show that the sum of these two gives you this expression. And I wanted to show you the proof, but I won't have time. But the proof is actually very easy. You can easily see that the sum of these two is the joint distribution of U and W. U and W are independent. U has an exponential distribution, and so you immediately have this. So it's actually a very simple proof. Okay, and now we have to show identification based on this equation. And I will explain it very quickly. We did it in two steps. First, we looked at the case where there is no censoring, and then the case with censoring. And the key idea is that we first need to identify the F0 and the F1. FW is not an issue because W is always observed. So the distribution of FW is identified. So we can identify F0 and F1, and we do that first without censoring and then with censoring. And once these two are identified, you can then show identification of phi 0 and phi 1. So let's maybe immediately go to the case with censoring. And the assumption we are going to make is this one, which is quite heavy. So it means that censoring is independent of unobserved heterogeneity, of the treatment, and of the instrument. We could relax it by assuming the more standard condition of conditional independence. We are not doing it because it complicates a bit the estimation procedure, but in principle it should be possible. But since it's already quite complicated, we decided to go for this more strong condition. Okay, so what we showed is that F0 and F1, if you have censoring, you can write them in this way. The usual trick with censoring, so you divide by the probability of the observation to be censored, and you only take the uncensored observations. Yeah? And this is an expression that is identified because the delta, the g, and then these variables here, they are all observed. Yeah? So that shows that F0 and F1 are identified. And once they are identified, you can then just solve this equation for the phi 0 and the phi 1. And that shows identification. Now, for estimation, now we are going to make a parametric assumption.
Don't worry. You can do this one.
Yeah?
Okay. Just pick up.
Okay. So, for estimation, so far I didn't make any parametric assumptions, so I assumed that everything was non-parametric, which works for identification, but for estimation we decided to make parametric assumptions, because otherwise you have an ill-posed inverse problem. I guess it can be done, but we didn't want to do it. So we simplified the problem by making parametric assumptions on the phi function, or equivalently on the lambda. This doesn't mean that the model is fully parametric. Actually, it is semi-parametric, because the F0 and the F1, they are still non-parametric. Yeah? So in this equation that I showed you, this one, the F0, the F1, and the Fw are non-parametric. And then we assume phi 0 and phi 1 to be parametric. Okay. So that's now what we do for simplicity. And here are a few examples of models. So we could, for instance, take a Weigel model. So remember that our lambda consists of two parts. There is the hazard up to the point where the treatment starts, and there is also the hazard after the treatment started. So you might take a Weigel for the first one and another Weigel for the second one. So that leads to a model with 4 parameters, and then you might also look at the formulas of the cumulative hazard or these inverse functions of phi's, and you can show that this is then the function of the two phi's, phi 0 and phi 1. Okay. So that's for the variable. You can also take, for instance, two log normals or any common parametric model from survival analysis. Okay, so the question is now, how do you estimate these 4 parameters based on the data? And so remember, the data look like this. We have the y's, the deltas, so these are the censored survival times and the censoring indicator. And then we have the censored treatment, the censored treatment indicator, and the instruments. Okay, so the estimation will be done in 2 steps. We will first estimate these non-parametric functions, the f0, the f1, and the fw, and then we plug these in the equation and we solve the equation. So here is the idea. So these are these non-parametric estimators, which very much look like the formulas I gave you before, except that there is now a g hat, and the g hat is simply the Kaplan-Meier estimator of the censoring distribution. And yeah, this is unconditional because we make the assumption that censoring is independent of everything. Okay, and then we plug in these estimators in our central equation, and we want to solve this for phi 0 and phi 1. And this we call m hat. Now, the problem is that this is an equation that depends on u and w. So it's not just one equation, it's an infinite number of equations. So how are we going to deal with that? Well, we are, for simplicity, we are going to take a grid of u values. So we are not solving it at every u value, we just take a finite grid. And for the w's, we take the data. The data, so the values of the instruments in our sample. And then we take a weighted average of this equation, the m theta hat squared. So we average over the w's and over the u's. And we add a weight function, p, which typically we will take equal to the exponential weight, and that's because we standardized the model in such a way that the unobserved heterogeneity has a standard exponential distribution. Okay, so this is now our, let's say, criterion function that we want to minimize with respect to theta, and so our estimator is going to be a minimizer of that function. Okay, and now we wonder what the properties are of this minimizer theta hat. So we showed the asymptotic normality. So it goes to a normal with square root n rate of convergence. And we also showed the consistency of the bootstrap. So we do a naive bootstrap resampling of our data, and this bootstrap estimator has asymptotically the same distribution as the original estimator. So bootstrap can be used to estimate, for instance, this covariance matrix sigma, which is actually difficult to obtain based on asymptotic theory. Okay, then quickly simulations. So here is the DGP that we consider. So we take UI and WI, so the unobserved heterogeneity in the instrument from an exponential 1 distribution. And then for the treatment, we take this formula here. So it depends on some noise, Ri, which is also a standard exponential, and then it depends, of course, on the U and the W. And we take U and W to a certain exponent, alpha and beta. Now the alpha is going to tell you how strong the endogeneity is. Because if Z and U are very much correlated, then we have a strong endogeneity problem. So alpha is saying what the level of endogeneity is. The beta is saying what the strength is of the instrument. Because we want the Z and the W to be correlated, and the more they are correlated, the better, because then the instrument is closer to the treatment. And so that's given by this value of beta. So it will be interesting to see what the effects are of alpha and beta on the estimation. Okay, and then for the model itself, we take either two Weibels or two log normals. Okay, and then in terms of censoring, we consider the case without censoring, just to take an easy situation for the first model. And then in the second model, we take Weibel censoring. No, sorry. We take exponential censoring times for the Weibel model, and we take log normal censoring times when the T's are also log normal. And then we chose the parameters in such a way that you have 20% of censoring. Okay. We did a lot of simulations, but of course I'm not going to show them all. So we have 3 sample sizes, 2 values of alpha, 2 values of beta, 2 distributions for T. And so yeah, this is a lot of cases. I'm not going to show all of them. I just have one table with results. For the optimization, we work with lots of starting values because the problem is not necessarily convex. So we take 100 starting values, and then we take the estimator as the one that leads to the smallest objective function. So that's to reduce this problem with local minima. Okay, and here are the results. So we have 2 sample sizes, 500, 1000. And I took here beta equal 1 for all cases, and for alpha I took 0.5. The alpha was the strength of the endogeneity problem. So what do we see? So we have here bias, standard error, and then coverage. So we see that overall the results are not too bad, but there is indeed a slightly worse outcome when the endogeneity issue is worse. So for 0.75, the results are worse than for 0.25, which is not surprising. So that's one issue, and then also we see, but that's not really given here, we see that the strength of the instrument is also important. But overall, the results seem to be okay. Okay, and then very quickly the data set again. So remember that we had data about burnout. So the T was the duration of medical leave because of burnout, and the Z was the time between start of medical leave and the beginning of the treatment. And this was endogenous because people could refuse to follow this treatment. And so for the instrument, we took the proportion of patients who are given the possibility to be treated by a medical center that was in charge of treating that patient in that year. So it was a proxy of the availability of treatments for a given patient. Okay, here are the results. So we take a viable model here and a normal model here. So we see two curves. The red curve is for patients who are never treated. So these are the ones for which the treatment is at infinity, let's say. And the blue one is for the ones that are treated immediately at the moment when they start the medical leave. Yeah, so z is equal 0 for the blue one and z is equal infinity for the red one. So what do the curves suggest? Well, we clearly see in the two cases that the ones that receive the treatment at time 0, they have a higher risk, a higher hazard. And higher hazard is good because the hazard tells you what the risk is of going back to work. And you want that risk to be as high as possible, of course. Yeah? So it means that this treatment for burnout is indeed effective. People go back to work quicker when they receive the treatment quicker. So that's good news for the insurance company. We also see that there are quite some differences in the shape between the two hazards, but that's because we use different models. So here it's survival, here it's somewhat normal. Yeah? But at least the conclusions are the same. So in both cases, the blue one is clearly above the red one. Okay, and here we have confidence intervals, pointwise confidence intervals for the difference between the hazards, so in fact the difference between these two curves. Yeah? So this difference is positive, and the confidence intervals suggest that the difference is significant for both models. Here it's everywhere significant, here it's a little bit insignificant at the end, but overall it seems to suggest that indeed there is most of the time a significant difference between never treated or treated at time 0. And the conclusions seem to be robust to the choice of model. So again, the shape of these two functions is quite different, but the final conclusion is the same. Okay, that's it. So here is a summary, and maybe an idea for future research, which we didn't do yet, is the case where this z is a general stochastic process. So in our case, it was kind of binary. It was 0 and then it jumped to 1. But you might have cases where z is a stochastic process that takes any shape. Like, for instance, alcohol consumption over a lifetime might be a continuous process, whereas we looked at a binary case. But that's more difficult, of course, and we didn't do that yet. That's all, and this is a reference, so it's now under revision for Journal of Business and Economic Statistics.
Thank you very much, Ingrid. If someone wants to make some questions to you.
Only a technical question, Ingrid. In some moment in your non-parametric estimators, in fact, you are using Kaplan-Meier intervals.
Sure, yeah.
So all the tools of Kaplan-Meier intervals can be applied there. No? For example, IID representation.
Yeah. I don't remember whether we used it or whether we did it by hand. I should check again the proofs, because it's my postdoc who did it. I didn't do it. I think, but I'm not sure anymore, that he did really the calculations himself without using the results for Kaplan-Meier integrals. But I should check.
I'm telling you because if I am not wrong, in our Scandinavian paper with Cesar, we give a global and general theory for representation of Kaplan-Meier integrals. Well, we can discuss. It's a
I will check.
technical question.
Yeah.
Okay, just have a very short comment. I'm very impressed with how difficult is the problem, and I'm not sure how the people in the insurance industry do these things. I guess they don't care about the endogeneity and the mistake because that's really quite. I have two little questions. One is really there was someone in the insurance company or in the industry interested in this, or it's just because we are statisticians, of course we want to do things right. So there is some interest in the practical people to do it correct?
Yeah. It was actually a very nice coincidence. So this data, they come from a Belgian insurance company. And in fact, I got the data from a person who was working for that company and who followed my course on survival analysis. Outside of his job actually. And he had to do a project for my course, and he used these data for his project. And he told me, I think there is a problem with my data, and it was exactly this endogeneity problem. So he realized that there was a problem, but he didn't know, of course, how to deal with it. So it was a very nice coincidence, because then, we talked about how to do it, we got the data, and
So thank you very much.